This video clip is part of the EPFL introductory course on information computing and communication. It is the seventh and last one in a set of video clips on computer architecture. Like the previous video clips, it gives another example of how computer performance can be gained, in this case by architectural rather than logic tricks. The performance of anything can always be increased in one of two ways, either by reducing the time or delay it takes to do something, or by increasing the throughput or the number of things done by unit of time. The previous clip gave an example of computer performance gained through reduced delay of logic operations. This clip gives an example of computer performance gained through increased throughput at the architectural level. A simple von Neumann processor, such as discussed in preceding video clips, normally executes instructions one at a time, as shown here. One can, however, imagine an enhanced processor in which more transistors are invested to build a second arithmetic unit and execute two operations at a time in parallel, as shown here, thus doubling the throughput of the system. But can you see a problem here? Let us see that problem. The problem is that there is a sequencing dependency between the next two instructions. The second one follows the first one in the originally sequential program for the very good reason that it needs a result from the first one. Unless one pays attention to that, the computation will produce wrong results and possibly crash the computer, or worse, cause something to break beyond the computer. The solution requires that an intelligent arbiter between the two arithmetic units detect when the second instruction depends on a result produced by the first one, and in those cases, execute them one after the other as in a basic computer with a single arithmetic unit. Thus, in practice, one cannot quite double the throughput of the computer. One can only approach a doubling while having to concede a small waste every time the computer hits a sequential dependency. So-called superscalar processors can be built with 2, 4, or even more parallel units to increase their throughput and thus speed up their computations. All modern computers do this. In addition, since they cannot know in advance what the outcome of a conditional jump might be, when they hit one, they perform in parallel the testing of the condition as well as both of the instructions that could follow the test, whether it comes out true or false. After the test, and both instructions have been executed, the result of the instruction not corresponding to the actual outcome of the test is thrown away as if it had never been computed. As in the case of investing in more transistors and power consumption to achieve faster operations, achieving higher throughput with more arithmetic units also costs more transistors and of course consumes more power, some of which is even wasted. In conclusion of this last clip, one can modify the architecture of a system to increase its throughput. This costs additional transistors and power consumption, but on the other hand, one can also build simpler processor structures to save power. These techniques belong to computer architecture, which is another branch of computer engineering.